So in this question, we've got copper sulfate as a roasted ore, which is going to be leached out with water. So coming into our system, we've got 1,000 kilograms an hour of this ore. So that's going to be our L0. And then a composition is given in the question. So we've got 20% copper sulfate. That's what we want to extract. So that's going to be component A. And we also know that 70% is insoluble solids. So B is going to be 700. And then the remainder is moisture or water. So that's going to be our solvent. So that's going to be 100. That's coming into stage 1. Now at the other end of our process, we've got fresh water coming in. And then later on it says for a water flow rate of 3,000 kilograms an hour. So the water flow rate here, C is going to be 3,000. B is 0 because it's an overflow stream. And A will be 0 because we're assuming it's fresh water. So there's no sort of impurities or anything. And what do we know? Let's look at the understream process, or the underflow stream down at the bottom. So we've still got our 700 kilograms of inner solid coming out, and we're told in the question that the underflow sludge retains 1 kilogram of solution per kilogram of solid. So in other words, we've got 1 kg of solid per 1 kg solution. Now it doesn't matter which way we write that around, it's obviously going to be the same. And that's actually what we define as N. So in other words, N is equal to 1. So this means that this is actually going to be a constant underflow process. Compared to the previous questions we did, they were variable underflow processes, so the N was changing. In this case, we're told that N is equal to 1, and we'll assume that that stays constant. So what that means is that we've got 700 kilograms of solid, so that means that our Ln stream, Ln is going to be 700, right? We've got, for every kilogram of solid, we've got 1 kilogram of solution. So that's going to consist of some copper ore as well as some water. So we need to figure out the concentrations of those. So for now we don't know A and C in that stream. However, we are told that the final underflow sludge must not contain more than 0.4% copper sulfate. So it's talking about this stream down here. And the question is a little bit vague. I'm not entirely sure whether that 0.4% refers to the concentration of the copper in just the solution or the concentration in the entire stream, so whether or not it includes the solid. Because it says the final underflow sludge, I'm going to assume that it's including the solid as well as the solution, and hence it means the overall concentration of A in that stream. So that's just sort of an assumption we'll make to sort of go ahead. So what that's telling us is that the amount of A divided by the total amount of material in that stream, well, that's going to be the amount of solid we have, 700, and the amount of solution we have as well, which we said earlier is going to be 700. So A divided by the total mass of material is going to be equal to 0.4%, or 0.004. And we can pretty easily solve for A. It's going to be equal to 5.6. And then we know that the total mass of solution in that stream is 700. So by doing a quick material balance, we can say that C is equal to 700 minus 5.6, which is equal to 694.4 kilograms. Okay, so now we can fill in our unknowns down in this final stream here. So we said A was equal to 5.6, and then C was equal to 694.4 kilograms. And then the last thing to do is just to figure out the composition of the extract stream coming out. We can do that really, really simply using mass balances. So we know that A, let me just go get my calculator. A up here is going to be equal to what comes in, which is nothing up here, and then 200 in here, minus the 5.6 coming out. So we're going to have 194.4 kilograms of A up here. B is going to be 0, because it's an overflow process. So B is equal to 0. And then C, again, is going to be what comes in minus what comes out. So we've got 3,000 coming in, plus 100, minus 694.4. So that gives us 2,405.6 kilograms. Okay. So far we've done pretty much exactly the same as what we did in the previous two questions. We've simply just solved the material balance around the overall system. And because this is a constant underflow process, there's two ways we can solve this. We can either use the McCabe-Thiele method, or we can use the analytical method. So in the question it tells us to use the right-hand rule, which wasn't something we covered in lectures this year, so we're going to use, I'll use probably both the McCabe-Thiele and the analytical method, because I haven't used those for a constant underflow process. So I think the easiest one to start with is probably the analytical method. So let's just get a new piece of paper. So the analytical method looks a bit like this. We've got y and x on our axes. We've got our y equals x equilibrium line. We've got the operating line, and we've also got the first stage, which has to be calculated separately. The reason we do our first stage separately is because it's not, when the solid comes in to our system, it's not in equilibrium with the other streams. So that's why we need to do that one separately. And then the analytical method basically takes the compositions at the second stage and the final stage, and it basically just works out the number of theoretical or ideal stages that would be required to get from here to here, and that's going to give us n-1 stages, because obviously we haven't thought about this first stage, so we just add on 1 to that answer, and that'll tell us the number of ideal stages. So let's think about what these points actually represent. This is going to be our starting point here. So that's going to be x0, y1. This is going to be our second stage. That's going to be x1, y2. And then this one down here is going to be xn, yn plus 1. So for the analytical method, really we only need to work out these 2 points, and then by using our graph we can figure out where the other values are. So let's go ahead and figure out those. It's probably easier to start with the final stage, because we've already figured out the composition of those streams from our mass balance before, whereas the second stage we hadn't really looked at. We sort of looked at the overall mass balance, not sort of looking inside the system. So xn, what's that going to be? Looking at our diagram, xn is going to be the concentration of A in this stream here, the final underflow stream. So that's going to be equal to 5.6 divided by 700, right? Our total mass of solution. So xn is going to be equal to 0.008. And yn plus 1, that's going to be the concentration of A in this stream here. And that's actually going to be 0 because we're using fresh solvent. So yn plus 1 is equal to 0. So that point is going to have the coordinates 0.0080. Okay, so that's the first bit done. Let's go ahead and figure out if you can figure out the coordinates for this second stage. So x1 is going to be the composition of this stream down here, so the underflow stream exiting the first stage, and we know that sort of by definition it's going to be in equilibrium with this stage up here, so we can actually say that y1 is equal to x1. right? This stream here is in equilibrium with this stream here, or those two solutions are in equilibrium. And we can actually figure out y1 from what we did earlier. Y1 is just the composition of this stream up here. So y1 is equal to 194.4 divided by the total mass of solution, which was 3,000. That's going to be equal to 0.0648. And then that's sort of by definition is going to be equal to x1. Okay, so the problem is we're now looking for y2, and we don't. That's going to be the composition of this stream up here, and we don't know that yet. So what we're going to do is we can take a mass balance around the first stage just by itself. We know this. We know a bit about this stream up here. We know about this stream, and we know the concentration of this stream down here. So we can do a few quick mass balances and solve for the concentration of this stream up here and figure out our y2, and that's going to help us to plot our curve. So let's draw up a mass balance for the first stage. So what's on the left hand side is going to be exactly the same as what we had before. So we've still got 194.4 coming out. B is equal to 0. C is equal to 2405.6, and then coming in we've got 200, 700, and whoops, C is equal to 100. Okay, and then we've got, this is going to be our V2 stream. This is going to be L1 coming out. Okay, we do know a little bit about this stream down here, so we know that the amount of B, the solid, is going to be the same, right? That's going to be 700 still. And we also know, we aren't given the amount of A and C, but we do know the concentration of that stream, so that's going to be equal to X1. That's going to be equal to Y1, which we said earlier was 0.0648. So we can say that A divided by 700, so I should probably explain this. We also know that from the question, N was said to be constant, so N is the mass of solid over the mass of solution. And we said that was going to be constant and equal to 1 throughout the whole process. So that means that our solid here is constant at 700, so we're always going to have 700 kilograms of solution. So A plus C is still going to be 700, so that means that the concentration of A in this stream is going to be A divided by 700, and we know that that's equal to 0.0648. So A then is going to be equal to 45.36, and then simply 700 minus that is going to give us our C. So that's going to be equal to 654.64. And this really helps us because now we can figure out how much A and how much C are in this V2 stream, and we can then figure out the concentration of that stream. That's going to give us our Y2. So A is going to be equal to what comes in minus what comes out, so 200 minus 45.36 minus, sorry, it's going to be what comes out minus what comes in. It's going to be 194.4 plus 45.36 minus 200. That's going to be 39.76. B is equal to 0, again because it's overflow. And then C is going to be equal to what comes out minus what comes in, so 2405.6 minus 654.64 minus 100. That's going to be, so that doesn't look quite right, I've typed that to my calculator wrong. That's going to be 2405.6 plus 654.64 minus 100. Yep, so 2960.24. So from here we can calculate our y2 composition. That's going to be equal to 39.76 over the total mass of solution in that stage. So 2960.24. So y2 is going to be equal to 0.01325. Okay, now notice something a little bit interesting here. The total amount of solution in V2 is going to be 39 plus 2960. That's going to be equal to 3000. Notice that it's also equal to 3000 up here. And when we started off, we had 3000 kilograms of solvent coming in. And if you look at the underflow streams, here we've got 700 kilograms of solution coming in, or 700 kilograms of solution in this underflow stream, and we've still got 700 kilograms of solution in this final underflow stream as well. So all that's telling us is that V, in other words the amount of solution in the overflow, is actually staying constant throughout all these stages, and this L is also staying constant. Apart from this first stage where it's different, but from 1 to n, L was also staying constant. So if we think back to our McCabe-Thiele diagram, we said that the operating curve had the slope L over V. So this we can sort of see from here that L and V are both staying constant. So therefore L over V is going to be constant, and hence our slope for our operating line is going to be constant. So that was just something I wanted to point out, but it doesn't really matter for our analytical method. But we do now have enough to plot those first 2 points on our graph. So let me just go ahead and grab some graph paper. Okay, so what I've done is I've just drawn a really quick sketch of our y equals x curve. I just plotted those 2 points that we had before. So I've labelled the first point here, so that's going to be equal to x1, y2. I've labelled that point A, and I've labelled the other point B. The reason for that is because we're going from point A to point B. This is like our second stage, this is our final stage. So it just shows sort of the direction, I guess, that we're going to be stepping in. And if you wanted to, you can draw an operating line between those 2 points. You don't need to for this stage, but if we were doing a McCabe-Thiele analysis, this would be the exact same operating line that we would draw. So it would have the equation L over V x plus whatever it is. So for the analytical method, we need 4 different bits of data. So we need YA, we also need YA star, or YA at the equilibrium point, so drawing a line up to the equilibrium line. So YA star. We need YB, which is just drawn straight across from there, and then same again, we need YB star. So once we've figured out those 4 points, we can simply just plug it into our analytical formula, and then we can solve for the number of stages. So if you think about it, YA, let's just write this out, YA is simply the y coordinate of this point here, so that's going to be 0.004. YA star, however, that's going to be this point up here. Now what we could physically measure it and graph it out, however, you'll notice that because this is a y equals x line, and all we're doing is drawing a line up at a constant x value, by the time we get to this point here, our x and y coordinates are going to be the same. So our x coordinate of this point is 0.0648. So we'll draw it up to here. Y is now equal to x. So YA star is going to be equal to 0.0648. I hope that makes sense. Basically, just think of it as on this curve, our y value is now equal to our original x value. So YA star is now equal to this. And then we do the exact same for point B. So YB simply going to be 0. It's on the x-axis. And then YB star, again drawing a line up and across, because the x coordinate is 0.008. when y is equal to x, y has to be 0.008 to lie on that curve. So yb star is going to be 0.008. Alternatively, if you wanted to, you could have drawn maybe another stage and then calculated across from here, and then another stage here and drawn across. But you really don't need to. You can simply just use the equilibrium relationship and the equilibrium line just to figure it out. So that just saves you having to do extra work. So that is all the data we need to do our analytical method, and it is simply, just scroll it up, it's simply a matter of just plugging it into the equation, which I'll just really quickly do. So the equation is n minus 1 is equal to ln yb minus yb star over ya minus ya star over ln yb minus ya over yb star minus ya star. Okay, so I get a value of 1.376, and remember, just go back to our drawing, remember this was from stage 2 to stage n, so we've simply just got to add 1 for that first equilibrium stage, which we didn't calculate. So simply n is going to be equal to 1 plus that, so 2.376, and that is your answer, 2.376 ideal stages. So what I might just do is, since we've already sort of calculated most of the numbers that we need, I might just go through and just redo that using the McCabe-Thiele method. Hopefully that won't take too much work. So let's get a new piece of paper. Let's construct our operating line. So we know yn plus 1 L over Vx plus V1 y1 minus L0 x0 over V. And remember, we talked earlier that L and V are now constant, so that slope's now going to be constant. So yn plus 1. Let's think about what L is. Let's go all the way back to our original mass balance. So, taking our last stage as an example, we can see that the overflow, or the V, is going to be 3,000. So that's 3,000 on the bottom, and then L, our underflow stream, was 700, right? A plus C. So 700. And it doesn't matter what stage we took them from. We could have taken them from when we did our stage 1 mass balance. We could use these numbers. Just the only thing we couldn't have done is used the L on our first stage, or our L0 value. The reason for that is, again, because the solid wasn't in equilibrium when we fed it into our system, so as long as you don't use that one, it's fine. You could have used any of the other streams in the process. And since they're staying constant, it doesn't matter which one you choose. So your slope's going to be 7 over 30. V1 y1. Should probably label these streams in our initial one. This was V1, that was L0. So V1 y1 is simply going to be the amount of A in that final overflow stream. So that's going to be 194.4. And then L0 x0 is again just going to be the composite of the amount of A in the initial underflow stream. So that's simply going to be 200. Again, you could figure out the concentration and then times it by L0. That's just, extra work. You can just simply read it straight off the mass balance. And then V, again, that's going to be constant. So that was, again, 3,000. So our operating line is going to be 700 divided by 3,000. So 0.233x. Don't want to forget the x there. That's going to be our slope, and then so negative 1.86 times 10 to the negative 3. So that is the equation for our operating line. So as a quick schematic, we've got our equilibrium line. We've got our operating line somewhere here, That's going to have that equation, and that was exactly what we sketched earlier when we did our analytical method, except if we're doing McCabe-Thiele, we want to draw that to scale. Okay, so we've got our y versus x plot, we've got our equilibrium line, and then we've got our operating line here. And remember that with McCabe-Thiele, we need to analyse that first stage separately. That's going to look maybe something like here. It should have a slightly different slope to the rest of the operating line. And what's sort of good to know is that by definition, this is going to be one equilibrium stage. From here to here. So therefore, when we draw our stages across, that's going to come across and then down, and we should hit the point for our second stage. And that's simply just because, by definition, we've solved for that second stage based on assuming equilibrium, and then this is simply an equilibrium line, so that's going to give us the exact same point. And then, as hinted in the question, it talks about you may want to expand the scale for the x-axis, and even though that's based using a different method, using the right-hand angled method, we sort of run into a similar problem in the McCabe-Thiele. So what actually happens is your operating line is down here, but your first stage ends up being way off the page, which makes the McCabe-Thiele analysis quite hard. So I'll show you what I mean by that. I'll just show you the one I did earlier. As you can see here, I've simply plotted the operating line with the slope that we first described, and I've drawn that up to our second stage point, and we can see that the first stage is actually all the way out here. So when I've done the stepping up stages, it's made it quite difficult. So that's why they suggest to sort of expand out the x-axis. So what we could have done, instead of doing what I've done, is you could have actually not drawn that whole first stage in at all, and you could have just simply concentrated on this operating line and expanded it out. And we can still do that. Just remember that when we get that number, that would give us the number of stages between our second stage and our nth stage. So we still need to add one ideal stage to that. So by getting rid of that first ideal stage in our diagram, that's okay. We just need to remember to add it on at the end. And it's always going to be equal to one ideal stage, because by definition, we've solved the equilibrium equation once. So it's going to be one ideal stage always. So we can simply just add one onto our answer from here. So really we have actually all the information that we need in order to solve the McCabe-Thiele method. We've got our operating line here, and we simply draw that operating line between our end point, or our nth stage point, and we draw that all the way along to our second stage, which we calculated back when we did our analytical method. So simply connecting these 2 points from here to here. That's going to be our operating line. Simply solve for the number of stages you need to do, and then simply add 1 for that first stage. Yes, that's how you solve a McCabe-Thiele for a constant underflow process, and that's also how you do it for the analytical solution. And just comparing the two numbers we did. When we did the analytical solution, we got, I think, 2.3 theoretical stages. When I did my McCabe-Thiele, I got about 1, 2, so almost 3 stages. So that looks pretty similar. However, it would have been more accurate if I sort of just not worried about drawing in that first point and simply just expanded the operating line a little bit, just to give me a bit more resolution, and then I could have probably solved that a little bit more accurately. But yeah, that's how you solve using the analytical method and the McCabe-Thiele method. And I think that's all the methods that we need to know. So hopefully you've learned something from these videos. Thank you for watching. Yeah, and good luck for Friday.